Okay, we jumped into 5.5, and now we're going to, instead of integrating, we've been dealing with e to the x's, but now we're going to talk about taking derivatives of functions other than e to the x's. So we're talking about other bases besides e. So I'm going to give you what this formula is for the derivative with respect to x. Now again, remember that u, a to the u is a function of x. So when I go to take this derivative, this is what it looks like. You're going to take a to the u, the function itself, times natural log of the base times the derivative of the exponent. Now, where does that come from? Well, it's actually pretty simple. This isn't one that I recommend that you memorize, because I'm not a big memorized guy. But here's what I could do. If I said y is equal to a to the u, well, I don't like the exponential functions. I'd rather throw in a natural log. So I'm going to throw in a natural log of both sides. And if I do that, let's rewrite this function. So if I rewrite it, I've got natural log of y is equal to u times the natural log of a. Well, natural log of a, wait a minute, if I go to take the derivative, I know how to do that. So this derivative, 1 over y times dy over dx, which is what I'm solving for. U is its own function of x. Natural log of a. Natural log of a is a number. A is a constant, so to take its natural log is just a number. So this derivative would be natural log of a times du over dx. So now to get dy dx by itself, I just have to multiply both sides by y. So I'd have y times the natural log of a times du over dx. So where does this formula come from? Well, the only difference is, here's a y, and we just put y back in. Y is the same thing. Y in the original problem was the same thing as a to the u. So I'm going to take the function itself times the natural log of the base times the derivative of the exponent. Well, it might take some doing. So let's go down and let's look at problem number 1. Let's put this in practice. So putting this in practice, f of t, I'm thinking quotient rule. So let's do this derivative. So derivative f prime of t. What do we have? So bottom, low, d high. So here's your d high. Here's where we're going to use our new rule. This is 4 as the base, 3 to the t is the power. So I'm going to start off with the actual function itself, 4 to the 3t. Multiply that by the natural log of the base, and it looks like I didn't leave enough room. And then I'm going to multiply that by the derivative of the upper bound, or the derivative of the bound, or sorry, the derivative of the exponent, wrong word, which would be 3. So low, d high, less high, 4 to the 3t, d low, square the bottom, away we go, t squared. There's your practice of cleaning that up. Now, if we go to clean that up, so we've done the derivative, that's the part that's going to give people the most trouble. Now, what could you do to clean it up? Really not much. I guess you could factor out a 4 to the 3t power. And if you did that, you'd have a 3t natural log of 4 minus a 1 over the top of a t squared. So there's your derivative, your first one where you did the derivative of an exponential function that didn't have an e as the base. Now my advice would be, every chance you have to make it have an e as a base, take it. Second one, okay, now we're taking the derivative of a log function that isn't a natural log. Natural log, remember, we're really good at, we like it. I'm going to tell you that with this thing, we're going to try to take advantage of what we know. We're good at natural logs. This one looks this way. So when I go to write down this rule for log base a of u, again, u is a function of x, a is a number, that derivative, 1 over natural log of a times 1 over a times du over dx. Now where does that come from? Well, again, I'm not a big memorized guy. Here's what I like instead. I'm going to say y is the same thing as log base a of u. And I don't like those logs. I'm going to do the change of base theorem, but when I do the change of base theorem, I'm going to, instead of do log of u over log of a, I'm going to do natural log of u over natural log of a. Now why do I like that? Because natural log of a is a number. I've got that already. So when I go to take my derivative, the derivative of y, actually let's even rewrite this thing. So my y that I really have is 1 over the natural log of a. That's a number, that's a constant, times the natural log of u. U, again, is a function of x. So when I go to take my derivative of y, dy over dx. Well, that 1 over natural log of a is a number, so that's just a constant along for the ride. Derivative of natural log of u, 1 over u times 1 over u times du over dx. Oh my gosh, and I look up here and I wrote this wrong. This should not be 1 over a. This should be 1 over u. My apologies. That should be 1 over u. So where'd we get it? Again, I'm not a memorizer. I am a change it and use what I know. And what I know are these natural logs, and every chance I get, I'm going to try to introduce it. So to that end, let's look at number 2. In fact, you know what? I'm going to do number 2 without even having that formula on my screen. Because let's look at this. So this thing, what I have here is I've got log base 8 of this thing. Well, let's immediately use our log rules to change this thing. So if I wanted, this is natural log of x to the 4th over x minus 5 divided by natural log of 8. There's my change of base theorem. I just went through and I fixed it. So this is really 1 over natural log of 8 times, now, natural log of x to the 4th over x minus 5. Let's use log rules. 4 natural log of x minus natural log of x minus 5. Well, now, if I said that's your y, so now take the derivative. Well, if you take the derivative, it's going to have 1 over natural log of 8 in it. 1 over natural log of 8 times the derivative of 4 natural log of x. Well, that's 4 times 1 over x times 1 minus derivative of natural log of x minus 5, 1 over x minus 5 times 1. Derivative is a piece of cake. So the key with this is don't try to memorize a formula. In fact, I wrestle every year with even showing that formula because we can work our way around it. And we're not memorizers. 1 over natural log of 8 times 4 over x minus 1 over x minus 5. If you wanted to get the common denominator, I guess I'll just go ahead and write it that way. So this is 1 over natural log of 8 times the quantity 3x minus 20 by the time we're done with common denominator over x and the quantity x minus 5 being multiplied together. So a couple ways you could go with either one of them. There's nothing wrong with either of those potential solutions. They're both adequate. What will be the standardized test answer? I don't know. I don't know. Probably common denominator, but it may not be. And then last but not least, now what's going to throw people off with number 3 is people are going to look at this one right away and they're going to go, oh, I see an exponential function because I've got x minus 3 being raised to the x plus 6. But what I need to do is I need to contrast what was up here. That exponential function, that theorem right there on the left, this a is a number. A is a number, okay? And if a is a number, and you try to use, you can't use that rule unless a is a number. Well, when you come down here and look, we've got x minus 3 being raised to the x plus 6 power. X minus 3 has a variable involved in it. We can't use that rule. So the only way to do this one is you got to do logarithmic differentiation. So let's do logarithmic differentiation. So if I do that, natural log of y is equal to, let's bring the x plus 6 down and make an exponent out of it, times natural log of the quantity x minus 3. Now when I go to take my derivative, 1 over y, dy over dx is equal to, how about a product rule? X plus 6 being multiplied by 1 over x minus 3 times 1, plus natural log of x minus 3 being multiplied by the derivative of x plus 6, which is 1. So now what do you have? You've got your dy over your dx is equal to x plus 6 over x minus 3 plus natural log of x minus 3. And if you wanted to get dy dx by itself, you'd have to multiply all of this by a y. Well, what's y the same as? Y is the same. Here, let's move this over so I can see it. Y is the same thing as x minus 3 quantity raised to the x plus 6 power. And yes, you could get a common denominator inside that red parentheses, but with the natural log, I don't think it's really going to do you any good to do so. So your standardized test answer is probably going to look just like what I have inside that box. So there we are. We're dealing with our complex exponential and log derivatives.